Hello, and welcome to one of the AP Biology Prerequisite content asynchronous videos. So this year, this is our first asynchronous video. So this year, what I'm going to be doing is for most of the content for AP Biology, I'm going to be delivering it to you asynchronously. So if you want to get some direct instruction, where I'm giving you the instruction, you're taking notes, I will provide you with a note template with most of the notes filled in, and then the direct instruction will be delivered asynchronously like this. That way, during our live sessions, we can have a little bit more interaction from you instead of just you passively listening to me. So our first lesson that we are going to be doing is going to be lesson on experimental design. And again, this is going to be more of the prerequisite content. So I'm going to share my screen with you. Okay, minimize that. All right. So again, what we're talking about here is experimental design. And what I'm going to start off with is a claim. And in this, the claim is your memory is better after exercise. So what we're going to do is we're going to run a test of this. So in AP Biology this year, often what you're going to be asked to do is create a claim and learn how to figure out how to test for that claim. So in this, we're going to test it. Okay, so I'm not going to have you actually do this, but let's say we were, and you could pause the video and try to see how the results will work for you. So you can lay your head down and rest for 30 seconds. So that's what we're going to start off with. Okay. So again, if you want to do this, you can pause the video and then come back in 30 seconds. Okay, now, again, you can pause the video and start a timer for 30 seconds to memorize these 10 numbers. Okay, so pause your video. All right, now, oops. You want to write down the string of numbers to the best of your memory. And this data table here is what you're going to use to record your data. So if I had a whole class of students, I would poll how many of them got 0, 1, 2, 3, 4, 5, 6. So you can go back to here, pause it, and see how many you got. So again, I would poll the class and see how many out of the students got 0, how many got 1, right? 2, 3, 4, 5, up to 10. And I'd graph that data. All right. Now, again, our claim was that exercise would improve memory. So this time we're going to exercise by marching in place for 30 seconds. So again, pause the video, stand up, and either do some jumping jacks or march in place. Just get your blood flowing, okay? All right. Now, get ready because I'm going to show you another 10 numbers, and you're going to remember them for 30 seconds. Oops. Okay. So, did you improve, stay the same, get worse? So again, I would probably poll the class again. We might show the graph of the data, maybe overlay it with the other graph. So some things that we can come through. Was our claim correct? Was our experiment a good experiment? why or why not? So you might be thinking, what were some things that Mr. Bradley's experiment did that were good? What were some things that were bad? What would you have done differently? So that leads us into our discussion on actually what is science and experimental design. So science, a lot of times it's kind of confused. It's saying like things are done scientifically. There isn't really, when you hear things are being done scientifically, often you're saying that they're being done in a very organized way. But sometimes science has been used to say that we are doing something for the benefit of humans, or you know, et cetera, et cetera. But ultimately, what science is, it's the search for explanation for what we see in the natural world. And I put the little notice that it requires factual evidence. So how do we get these explanations? Well, we look for patterns or similarities with something that we already understand. And these patterns will lead us to, well, you guys are going to learn there's going to be an intermediate that we call a claim. So we make a claim that we can look at. So you might think, oh, you know what? When I get up in the morning and I swim and then go to school, I feel like I'm much more alert and much more ready to go. So maybe what I'm going to test is being more doing exercise. Is that going to help in a measurable way improve memory? So you might come up with a hypothesis. So hypothesis is an explanation of a specific natural event or phenomenon based on observations or patterns. So the important thing is that this is testable and falsifiable, meaning observations and other factual evidence should be gathered in order to support or reject it. And ultimately, you want a good approach of a good approach of a scientist is actually to think of your hypothesis as being incorrect, and you're looking for every possible way in which your hypothesis would be incorrect, because you don't want to just go out and look for evidence that's going to only support your hypothesis. You want to find ways in which your hypothesis would be held wrong. So here is our explanation. Exercise makes you more alert and therefore helps you improve memory. If you want to be more into a specific format, you could say it's an if-then statement, but with a because. So it's not just an if-then, but it has a because component as well. So the next part of this is that there is an experiment. And an experiment is a test for a hypothesis, or you could also say it's testing a claim. And again, I'll get into what a claim is in a little bit. A claim could be a prediction. A prediction is something that should happen in an experiment based on a specific experiment. So that's how, more specifically, it's different than a hypothesis. So a hypothesis is more a general statement, whereas a prediction is based on what's going to happen if I carry out this particular experiment. Hopefully you understand that. That's a key thing that kids get confused, is the difference between a prediction and a hypothesis. A prediction is going to explain what's going to happen in an actual experiment. A hypothesis is a generalized, if you're more alert, you're going to have better memory. And if you exercise more, you're going to be more alert and have better memory. But there's lots and lots of ways to test that. So our prediction for this experiment was, after 30 seconds of exercise, you will see improvements in how many numbers you can remember. Look about specifically what we did in the experiment and how we specifically measured the outcome. Most things in nature cannot be definitively explained. So when you have continuously shown a hypothesis to lead to correct predictions, the explanation is considered a theory. So one of the things that gets confused is the difference between a hypothesis and a theory. A hypothesis is tentative. It's falsifiable. it's narrowly focused. Theories are well established. They're very broad, and they're probably fact. Again, I'm not saying a hypothesis is probably false, it's possibly false. Theories are probably fact. And again, they're going to be broad, more well established. Now, not everything has a theory that goes into it. There wouldn't be necessarily a theory that we would apply to our idea here of exercise improving memory. But there are going to be theories on other things that we will talk about. So this is a helpful diagram of basically how scientific inquiry works. So you start usually by making observations. And here's a key thing I want to talk about is doing something, doing science isn't necessarily doing this whole thing. Just making observations is doing science, and learning how to make observations so that you are honing in on specific things or looking for a pattern or a cause and effect. That allows you to make a claim, make a prediction, and ultimately develop a hypothesis. Then you're doing science, but you're doing science just by making observations. So you develop a hypothesis and then you run a test. And again, it doesn't necessarily have to be developing a hypothesis. You can do a test of just a claim. The claim, so again, what I might say is in certain cases, as it says here, further alternate hypotheses, the hypotheses in some case is the outcome. And notice it's a cycle. You don't ever really stop in the case of science. Science doesn't stop. You're always looking to improve upon and have a better understanding of whatever observations there are in science. So just having a theory allows you to hone in and have a better understanding of what observations you are making. So if I can give you the example of like with evolution, when you see things like the pattern of bones in the arm of a human and a chicken and a whale having the similar pattern of one bone in the upper arm, two bones in the lower arm, and then tiny bones in what would be the wrist, and then other things coming out from there, you can say, oh, there's a pattern that I'm seeing there. And the theory of evolution helps you to understand that. Why to that? Why was that pattern there? The last thing we're going to talk about is developing a valid experiment. So what actually makes something a valid experiment? So first off, when you do a valid experiment, there's lots and lots of ways you can experiment. But generally, when you're testing a hypothesis, you want to try to hone it down so that you're looking for one specific cause that will generate one particular effect. But again, this isn't just the one way of doing science, it's just a specific way. So the first part is the coming up with your independent variable, the thing that you're going to test, the thing that the scientist is going to manipulate or change. So in a valid experiment, all the ways the independent variable is applied are called the treatment levels. So that's the way that they are changed. So maybe you're testing temperature. So all the different temperatures are all your different treatment levels. In some cases, you can have experimental treatments, and in some cases, you might have a controlled treatment. So in the case of like temperature, if you're testing temperature as your treatment level, you don't have necessarily a control temperature. You just have a whole bunch of different temperatures and you're just comparing each one to the other. And if you wanted to run a control treatment, maybe what you would do is have something where it's not going to be affected whatsoever. So you can't remove temperature, but you can remove, like maybe what you're talking about is what's the effect of temperature on the metabolism of a yeast. Well, maybe you in a control treatment, maybe just take away the yeast so that you can see, well, now I don't have any any outcome. So I'm just changing the temperature and I'm measuring the outcome of that. And you can see, well, I have no expectations for that. But there's other things where, like if you're learning about here's a particular medicine or a vaccine and I want to have a placebo group, that's ultimately a control treatment. So in this case, exercise type, what we're saying is rest or no exercise is going to be our control, and then our exercise is our experimental group. Then we have our dependent variable. This is what's affected as a result of manipulating the independent variable. It's what gets measured and reported as changing. So in this case, our dependent variable is the number of numbers that you remembered. So ideally, these effects are measurable. We also need them to be valid. So the way you do that is by having multiple trials. So I could have multiple times trying to remember those numbers. And that actually might have been something that was an issue here. I only had the second trial, you knew what was coming up. So that can have like an anticipation can actually have an effect on how much you remember. So if you can like kind of do this a bunch of times, you can get honed in on more effective data. If I only measured you individually, that's not a big enough sample. I'd want to have a whole bunch of different people, and that's a sample size. So as it says here, sample size must be large enough to show a lot of the measurement comes out close to the average, referred to as showing a trend or significance. And we identify the size of the sample and other information about it, like the average or mean. So the difference between trials and sample, trials are the experiment performed multiple times, whereas a sample is having many different data sources you are testing. So different people, amount of yeast, things like that. So that's something that you have to keep in mind when you're doing testing. Do I have a large sample size or do I have multiple trials? Should I have multiple trials? If you can't perform multiple trials, you want to have a big sample. If you don't have a big sample, then you want to have multiple trials. The other thing that you could affect your dependent variable, in order to test only the independent variable, you want to keep all other things, what we would call confounding variables. You want to keep those things that could have an effect on it. You want to keep those as constant as possible throughout each trial. So if temperature is going to affect it and you're not testing temperature, keep the temperature constant. If the volume of something is going to affect it, keep the volume constant. So for us, the amount of time to memorize, we try to keep constant. The sample was the same for both, an amount of numbers to memorize, and the size of the numbers that you were using to memorize, like no more than double-digit numbers. All right, so we'll stop there.